Welcome back to The Explainer. Today, we're diving into one of the absolute most fascinating turning points in the history of physics. I want you to cast your mind back to 1913. The structure of the atom was still, honestly, a huge mystery. Scientists knew there was this heavy, positively charged nucleus in the center and negatively charged electrons somewhere on the outside. But how they actually interacted? Massive puzzle. Enter Niels Bohr. This Danish physicist proposed an atomic model that became a brilliant transitional stepping stone. It famously solved the mystery of the hydrogen atom, and by doing so, literally paved the way for modern quantum mechanics.
So here's the fundamental question that hooked early physicists. How on earth do you model something you can't even see? At the time, physicists were wrestling with this incredibly frustrating classical physics dilemma. According to classical electromagnetism, if an electron is orbiting a nucleus, it's constantly changing direction. That means it's accelerating, and an accelerating charged particle should, theoretically, radiate electromagnetic energy. But if it's constantly radiating energy, it should lose momentum and spiral rapidly inward, crashing right into the nucleus in a fraction of a second. So if we play by classical rules, atoms shouldn't even exist. We shouldn't exist. To solve this invisible puzzle, Bohr realized he had to just throw out the classical rulebook.
Okay, let's dive into this. To stop the electron from crashing into the nucleus, Bohr introduced a radical first postulate. He proposed that electrons revolve around the nucleus in discrete, stable orbits. And the real magic here? While they're in these specific orbits, they do not radiate any energy at all. They act in complete, utter defiance of classical electromagnetism. In this planetary-style model, the electron maintains a set distance, a radius we'll call r, held in a perfect, unchanging balance. Now, the terminology Bohr used here is super fascinating. He called these specific paths stationary orbits. Obviously, it's not that the electron is physically standing still. It's moving incredibly fast, but its energy state is stationary. The electron is strictly forbidden from existing in the space between these discrete paths. You can think of it like standing on a ladder. You can stand on the first rung, or you can stand on the second rung. But you absolutely cannot stand on the empty air in between.
So how did Bohr decide where these allowed rungs on the atomic ladder actually were? Well, he quantized the angular momentum of the electron. His new equation dictated that an electron's angular momentum, represented by L, can't just be any random value. It mathematically has to be an exact integral multiple of the reduced Planck's constant. You see that little n in the formula? That's the principal quantum number. It can be 1, 2, 3, and so on, but never, ever a fraction. This was a massive conceptual leap. It tied the physical orbit of an electron directly to Max Planck's newly discovered quantum rules.
And this brilliantly illustrates what happens when an electron decides to change its orbit. Bohr stated that an electron only loses or gains energy when jumping between these allowed levels. When it drops from a higher energy state, let's say E2, to a lower one like E1, it radiates that precise energy difference as an electromagnetic quantum, basically a photon of light. And the frequency of that emitted light is perfectly determined by this Planck relation. It's just a beautifully clean explanation for why atoms only emit specific, discrete colors of light. Transitioning over to the actual physical mechanics of the atom. Imagine a single electron of mass m and charge -e revolving at a velocity v around a heavy, positively charged central nucleus. Bohr needed to prove that his quantized orbits could actually exist in a state of mechanical balance. To pull this off, Bohr assumed a circular orbit for convenience, and he elegantly balanced two competing forces. On one side of the equation, we've got the centripetal force. That's the mechanical force required to keep a mass moving in a circle. On the other side, we have Coulomb's law representing the electrostatic attraction, which is pulling the negative electron inward toward the positive nucleus. For the orbit to be stable, these two forces must be perfectly equal. By locking this force balance together with his quantized angular momentum, Bohr was actually able to calculate the exact allowed radii and velocities for an electron in a hydrogen atom. Now here is the really crucial point. This wasn't just a neat theoretical trick. This exact force balance, combined with that energy jump postulate, provided the very first theoretical justification for the Rydberg formula. Before Bohr came along, scientists knew this formula worked experimentally to predict the exact wavelengths of hydrogen's visible light emissions, but they had absolutely zero idea why it worked. Bohr's model derived this exact empirical formula from scratch, perfectly predicting the Balmer series of hydrogen emissions down to a fraction of a percent. It was an absolute triumph for the new quantum theory. But, Bohr didn't want to completely abandon the classical physics that had served science so well for centuries. So he introduced the correspondence principle.
This principle states that for very large electron orbits, where that quantum number n is huge, the bizarre quantum jumps start to blur together, and they essentially match the predictions of classical Maxwell theory. Bohr brilliantly proved that classical physics wasn't entirely wrong. It was just a specialized approximation that only worked when you zoomed way, way out from the quantum scale.
However, as incredible as this 1913 model was, we have to look at where the Bohr model fails. Because while it perfectly described the single electron hydrogen atom, it completely failed with multi-electron atoms. It couldn't explain chemical bonding in molecules, it completely missed fine and hyperfine spectral structures, and it had absolutely no explanation for electron spin. Let's look exactly at why it fails so spectacularly for anything larger than hydrogen. Bohr's success rested entirely on the idea of a simple central force from a single nucleus pulling on a single electron. But the moment you add a second or third electron, they start repelling each other. The outer electrons see a partially shielded nucleus because the inner electrons are physically blocking them. This electron-electron interaction completely destroys the simple central force pillar of Bohr's derivation. The math just falls apart.
Which brings us to a direct angular momentum showdown between Bohr's early theory and modern reality. Let's look at the atom's lowest energy state, the ground state. Bohr explicitly predicted that the ground state angular momentum is equal to 1 reduced Planck's constant. I mean, it has to be, right? His rule was n times the constant, and n starts at 1. But modern quantum mechanics definitively proves that for a ground state hydrogen atom, the orbital angular momentum is actually exactly 0. So Bohr's foundational assumption was, unfortunately, mathematically incorrect. And the differences don't stop there. Let's compare how we view electron location. The Bohr model locked electrons into fixed, two-dimensional circular orbits. It viewed the electrons strictly as a little planetary particle on a track. But in the 1920s, Erwin Schrödinger developed a vastly more accurate model utilizing wave functions. The Schrödinger model completely discards the idea of a fixed path. Instead, it shows that electrons exist in three-dimensional probability clouds, which we now call orbitals. We don't know exactly where the electron is, only where it's likely to be found. Which leads us to the final nail in the coffin for the literal interpretation of Bohr's fixed orbits. Bohr's model assumed you could know both the exact position of an electron, meaning its specific orbit, and its exact momentum simultaneously. But the later development of Heisenberg's uncertainty principle proved this is a fundamental impossibility in nature. The wave-particle duality of the electron means that the more precisely we know its position, the less we know about its momentum. So Bohr's cleanly drawn circles essentially violated the very laws of the quantum universe that he helped discover. Yet, despite all these flaws, we still teach the Bohr model today. Why? Because it's an absolute masterpiece of scientific transition. It introduced the world to quantized energy states and brilliantly solved the hydrogen spectrum when literally no other theory could. So, I'll leave you with this thought-provoking question. As we continue to develop even more advanced theories in physics, might our current, incredibly complex quantum mechanics one day look as beautifully primitive to future scientists as Niels Bohr's incredible 1913 stepping stone looks to us today? Thanks so much for joining me on this explainer, and as always, keep questioning the universe around you.